Hello, this is Dr. Muhammad, and this is another class under Dynamics of Structures. And today I'm going to talk about the multi-degree of freedom systems. For short, we use MDOF. So this topic for today, it is considered to be a new topic because before we were talking about the single degree freedom system. From today on, we are going to talk about multi-degree freedom system. So it is considered to be like a paradigm shift in how we are handling dynamic problems in general, but in the same time it retains all the basic principles that already we have explained before regarding single degree of freedom system. Today I'm going to give an introduction and giving some concepts and main and basic principles for MDOF, and then I'm going to talk about the general equation of motion, and after that, which is controlling or going to describe for us the equation of motion for the multi-degree freedom system. After that, I'm going to talk about the first case that we are going to handle, which is undamped free vibration. Pretty similar to what we have explained before regarding single degree freedom system. We started with undamped system, and then we went mostly to the damped system and investigate more and more. So let's go now for the first part, which is the introduction. Okay, so before saying anything here, we need to, let me check here. Okay, for the introduction, we need to be, first we are going to give some important definition for what we have done before in order to know what is the difference that is going to be there between the single degree freedom system and our multi-degree freedom system. So first of all, in the single degree freedom system, we were talking about single coordinate. Single coordinate means that we were having only one coordinate that we are interested in, which is the displacement in this direction, whether in this direction or right or left, but we are having one or single degree freedom system. We call it single coordinate. This single coordinate can be used to describe the motion. Okay, so we were using the equation of motion for only one direction at this level. In this case, a single differential equation of motion is used to obtain solution, and this is an important issue here that is going to give us the difference between single degree freedom and multi-degree freedom. That is, as long as we have only 1 degree freedom, then we are going to have only one single differential equation that is going to be used in order to describe the motion of this SDOF. However, in the general case, in reality, we are not facing SDOF commonly. Okay, the common case that we are going to see or to face is another type of system. We call it the continuous system. In this continuous system, we're going to find infinite number of degrees of freedom, which is totally different than the SDF. For example, if we have a beam, as you can see here, so this beam, it has infinite degrees of freedom because every point here, every point is considered to be a degree of freedom, or I mean that every point in the vertical direction, for example, if I'm talking about the vertical direction, it is considered to be a degree of freedom, and we need like a differential equation to describe it, right? So this one is, we call it, it requires complex mathematical computation. Complex, or it requires complex mathematical computation, because we are dealing with infinite number of degrees of freedom, right? Okay. After that, something in between that is we are going to study from now on is related to the multi-degree of freedom system. the multi-degree of freedom system. In this multi-degree freedom system, we are going to assume it is possible that, or it is possible to describe the structure with a finite degrees of freedom. Finite degrees of freedom. So the keyword here is finite. Means that our MDF is going to be different than the previous one, which is the continuous system, in such a way that we are having specific, particular degrees of freedom that we know them well, and we are going to describe the motion of these particular masses or add these particular degrees of freedom mathematically. Then in this case, we are going to avoid the complex mathematical computation that present in the case of the continuous systems, right? So based on that, we need to define something that is going to meet this description, which can be described by a finite degrees of freedom. So we found that there is a kind of a prerequisite that is needed in order to maintain or meet this requirement. The physical properties of the structure should allow to describe the displacement response in terms of the displacement amplitude of some specific or selected points. What is the meaning of this? The physical properties. What is the meaning of this physical properties? It means that we are going to find the arrangement of masses and stiffness in our system allow us to describe a particular equation of motion at particular level or at a single or particular degree of freedom. So this means that, for example, for building structures, we are going to have the masses generally are at the levels of the floors. This means that the masses are concentrated. And we have mentioned about this before in the beginning of this course. We said that whenever we have concentrated masses at certain point, then we can say it is lumped mass, right? Means that the mass is going to be concentrated at specific point, and this would make it very easy for us to describe the motion. Okay, so we can say that our system is going to be like this, concentrated mass at different level. These levels are the levels of the floors. So that's the meaning of physical here. Physical means that the masses, whether they are concentrated or not, and in the same time the stiffness should be arranged in a symmetric way so that we can describe the motion conveniently with different and individual equations at each level. So again, the physical properties of the structure allow to describe the displacement response, because we are interested in displacement, okay? Displacement response of the dynamic loading, okay, or the dynamic motion. In terms of the displacement amplitude, what is the meaning of displacement amplitude here? Whenever this structure is going to move in this way, the masses are going to be displaced horizontally. This is what we call it amplitude. This is, for example, A3. This is A2. This is A1. This is the amplitude of the mass. Okay, so we are going to describe the motion of this mass through the amplitude of the displacement at some specific or selected points. Okay, so this is the definition of the multi-degree freedom system. Remember well the word finite and the word physical properties and the lumped mass. Okay, these are important things that we need to consider. Okay, now let's go to the next slide. And we are going to talk in this slide about an important concept that is always used whenever that we talk about a multi-degree freedom system. And this concept, we call it shear building. Shear building. This shear building means that we are having a specific type of building, that is going to allow us to idealize the multi-degree freedom system in the way that we have explained before, which is the physical properties that we have mentioned before. The masses to be arranged in concentrated masses, and the stiffness is going to be arranged in a way that we can use the mass and stiffness to describe the amplitudes and so on. So shear building is considered to be one type of structures that can be idealized. That's the point here. Idealized means that we can handle it. We can idealize it as MDOF, multi-degree freedom system, as justified from its physical properties. Okay, remember physical properties, mass is concentrated and stiffness and so on, is what we call it shear building. Shear building. You're going to find in every textbook, whenever that we are starting or whenever they are talking about multi-degree freedom system, they are going to mention about the shear building. Okay, the shear building. Then we need to understand it more, and we need to elaborate on the basic principles related to this shear building. In order to build upon these basic principles, the equation of motions and the big picture of the multi-degree freedom system. Now let's go to the definition. The definition of this shear building. Okay. So now, regarding the definition of the shear building, we can say it is a structure in which there is no rotation. Take care of this. No rotation. We are talking about structure that has no rotation at the horizontal levels of the floors. So if we have a structure, something like this, and we have floors, as you can see, so we are not expecting that the floor girders to do something like this. It's not expected. We are expecting only that the floors are going to be displaced horizontally. This is what we are expecting from the structure. Okay, so there is no rotation at the horizontal levels of the floors. In such a case, okay, because of this, because there is no rotation, so what is the consequence of this? The deflected shape of the building will be similar to that of a cantilever beam subjected to shear forces only. Whenever we have a cantilever beam, consider it like this, and we have like different masses, for example, and it is like applied or subjected to vertical forces. You can just rotate it 90 degrees and put it like this, and you're going to understand that if we could assume, or if we are presuming that this building is shear building, then we can simply say that it can be represented by this way, which is a cantilever. And this cantilever, only vertical, horizontal displacement are going to be considered under the forces that is going to be applied on the system, right? So that's the meaning here of no rotation, and then from this no rotation we are going to have the concept of the cantilever beam subjected to shear forces only. Shear forces only. Take care of the word shear. Okay, it's not flexural. Okay, it is shear only, because we are expecting the forces applied in the system to be horizontal, and we are expecting that the resistance of the system, which is the cantilever parts here, different cantilever parts, to be resisting these forces through shear resistance or shear stiffness. Okay, only. Okay, that's the word, only what it represents here. Okay. Now, if we are going to talk about this, we need to mention about some assumptions that consider to be important for us to derive the equation of motion. So we're going to talk here about assumptions for shear building deflected shape. Okay. If we are going to look to this building, as you can see here, we have 3 floors. Masses are concentrated at the floor levels, and we have columns, as you can see here. If we're going to make the idealization, we said it is as if it is a cantilever. Let's assume cantilever column here with concentrated masses at the floor levels, as you can see. Okay, so number one, or the assumption number one, that is going to be related to the shear building is the total mass of the structure is concentrated at floor levels. This is number one. The total, take care of this word, total mass of the structure is concentrated at floor levels. This means that we are going to say and assume that the masses that is going to be represented by the floor or by floors, okay, it is considered to be the total mass of the structure. Maybe you are going to ask, what about the column masses? It is neglected here. Or we are going to assume that the masses of the column is going to be added, the upper half and the lower half of the column going to be added to the floor level. So this means that total mass is important here. As I said, this is considered to be a key word, total mass. It's not part of the mass or not portion of the mass. Okay, so what does it mean up till now for regarding this issue? This assumption transforms the finite number of DOF to a structure having as many DOFs as it has lumped masses at floor level. Okay, what is the point here that we should take care of? That is transforming this system from being infinite with having infinite number of degrees of freedom, because if we have a column and we said that this column, the mass of the system, is going to be represented as continuous mass, this means that every single point is going to have a degree of freedom, right? Then we have infinite number of degree of freedom, okay? But here we are making a nice idealization. We said, no, it's not like this. We are going to make masses, big masses here at the floor levels. This means that we need only 3 differential equations or 3 equations in order to represent the motion of the entire system. However, here we have infinite number of equations. This is going to be mathematically and computationally demanding. However, here it is going to be controlled easily. We may solve it analytically easy, right? So this is the key of the total mass. The meaning of total mass, as I said, the key word or the interpretation of it is the total mass of the structure is concentrated at the floor level. It means that we are going to transform the problem from being a system, from a continuous system to a discrete system. Okay, this is the meaning of total mass is concentrated at floor levels. Okay, so we are changing the system from continuous system to discrete system with infinite number of degrees of freedom, to another system that is having degrees of freedom at floor levels only. Okay, this is assumption number one related to the shear building. Okay, now let's go to the next assumption. We have 3 assumptions actually for the shear building, and we are going to talk about them in a row. So assumption number 2 is related to the beams are infinitely rigid as compared to the columns. Again, there is a key word here, infinitely rigid. So we are going to consider, or we are considering that floor girders, as you can see, they are infinitely rigid compared to the columns. what is the meaning of infinitely rigid here? This assumption requires that joints between beams and columns are fixed against rotation. Okay, what does it mean? How it will help us in our derivation of equation of motion? This implies two main things. Number one, whenever there is no rotation, or whenever we assume that the joints are having fixed or being fixed against rotation, this means that, as you can see here, the relation between the column and the girder is going to be always perpendicular, as you can see. There is no rotation. It is not going to be something like this, for example. Okay? It should always be right angle. Okay? So this right angle means that there is, that right angle, this is by rotation here. Maybe it is not right here to make this. Here, if we have the girder to be something like this. Okay? Column needs to be perpendicular to it, like this. But if we have another case, which is something like this. This is the girder, and this is going to be the column, for example. This means that there is rotation here. Okay? This rotation is not allowed. Shear building does not allow this rotation. It is always going to be perpendicular to one another before and after motion. So this is the case before the motion. This is the case after motion. Okay? So why? What is the significance of this assumption? This means what? That only horizontal degree of freedom is allowed and no rotational degrees of freedom are included. This means that we are not going to be concerned with what is the rotation at this point or at this joint. We know that rotation is 0. This means that we are going to eliminate all the equations related to describing the rotational motion. Okay? So this is very important concept, that we are dealing with horizontal movement only. So whenever that we say the assumption of the beams are infinitely rigid as compared to columns, this means that we are dealing with horizontal degrees of freedom, not rotational degrees of freedom. Okay, this is number 2. This is assumption number 2. Okay. Assumption number 3, it is related to the deformation. The deformation of the structure is independent of axial forces present in the columns. So now the keyword is axial forces. What is the meaning of this? This means that the rigid girders will remain horizontal during motion. Will remain horizontal during motion. This makes horizontal forces only are required to be included in the equation of motion, and no need for the inclusion of axial forces. Okay? Because we are going to have horizontal forces that is going to be applied on our system, and these forces are going to be changing with time, f2 t, for example. So this means that we are going to put in our equation, do you remember the differential equation? We have left hand side equal to right hand side. In this right hand side we put always the forces. So these forces that we are going to put in our equation of motion, or in the differential equation, is going to be concerned with the horizontal forces only. But we are, or in the same time, we're not going to consider any vertical forces or axial forces in columns. It is going to be excluded. We're not going to assume that it affects anything regarding the differential equation or the motion of the horizontal girders. Okay, so this means that the rigid girders will remain horizontal during motion. Okay, and this makes the horizontal forces only are required to be included in the equation of motion, not the column axial forces, as we have mentioned, because actually the axial forces are not going to make anything for us. I mean that the axial forces of column will not affect anything for the beam itself, because it's perpendicular to it, so it is going to make we are not expecting something like this to happen, okay? Because of the axial forces in this column is going to be heavy, for example, so it is going to be compressed and then there is rotation. No, we are not going to consider this kind of stuff, okay? So that's the meaning here regarding this this issue. Okay, now let's go to the meaning of the name itself, which is shear building. Shear building. So shear building means, okay, so shear building, sorry, okay, so shear building means that the reason for the name itself of shear building, shear forces only causes the deflection, because we have shear forces only, okay, causes the deflection. No rotation at horizontal levels. No rotation at horizontal levels. So this is the meaning. From here comes the name of shear building. We didn't call it only building or flexure building, for example. It is shear. Shear because shear forces only are going to be concerned. No axial forces, no rotation, no other type of degrees of freedom except horizontal movement or motion and horizontal forces. This is what we are going to be concerned with. Okay. Okay. So this is regarding, these are the main concepts that we are going to have for our system. Based on the above assumptions, we can derive the equation of motion for a multi-degree of freedom system. Okay, we are going to derive it now, and we are going to see that how we are going to derive the equation of motion. Okay, now let's go with this equation of motion. Okay, let's go to the next one. Okay, now we have this equation of motion, and we need to put first the mathematical model. We're going to use a 3-story building, as you can see here, and we are going to make the representation to be clear for us after that. Okay, so we are going to find that if we have a shear building, as you can see, with masses concentrated at floor levels, this means that we are going to have mass M1 and M2 and M3 at floor level 1, 2, and 3. And then we are going to have forces applied on the system, okay, forces applied on the system, which is going to be horizontal forces also applied at the floor levels. Each floor is going to resist the motion through two things. First, it is going to resist by elastic resistance, which is represented by the columns at each floor. So at the first floor, for example, we have K1, which is considered to be the total resistance of all columns in the first floor. So if we have two columns here, we have K1 over 2 and K1 over 2 for the right column. Similar for the floor level number 2 and floor level number 3. Well, based on that, we are going to have resistance based on the columns, the shear resistance of columns. Okay, so that's the important thing here. In the same time, we have damping that is going to be represented, okay, by this dash dot designation, and it is going to be related to each floor. So we are going to find that we have damping coefficient C1, C2, and C3 for the floor levels, and we are going to find that it is going to resist the motion. We have damping for each floor or at each floor. This damping, as we have explained before, it comes from different levels. We have material damping, we have element damping, component damping, and we have structure damping, hysteretic damping. Different types and sources of damping are present in our model. So based on that, we are going to find under these motions, we're going to find that the structure is going to be displaced, or the floors are going to be displaced U1, U2, and U3 horizontally under these loads. Okay, so this means that we are going to have horizontal movement at each floor level. Okay, then we are going to make the idealization here. Okay, we are going to make the idealization, which is going to be, as we said, as a cantilever column. This idealization of multi-degree freedom system, this is the multi-degree of freedom system idealization. In the first floor, we have K1, which is the summation of all forces or resistance or stiffness from floor 1. And then we have K2, which is the resistance or stiffness for the second floor, and K3, the third floor. Forces are going to be applied F1 of T, F2 of T, and F3. Take care, it is dynamic force, so we have T here. Okay, it means that it is changing with time. We're not applying static forces, otherwise there is no dynamic motion and there is no response that we should obtain. It is dynamic force that is changing with time, and the rate of change is not so slow to the point that it's going to be static. It should be dynamic. Okay, and then we are going to have displacement, as you can see here, U1, U2, and U3 based on the floor level and the stiffness and the damping that is going to be there. Okay, actually here we are going to have I'm talking about stiffness here. Okay, I'm talking about the stiffness because we need to understand it before going into the mathematical model. So if you look here, you're going to find that each mass is being we are going to apply the forces on each mass, and we're going to look to it as a free body diagram. Okay, in order to understand how the forces are being applied on the system and on the masses. Okay, now forget about the damping. I'm going to talk about the case where the resistance coming from the stiffness only. Okay, so let's magnify this. Magnify this this figure, and as you can see here, I think this is okay. So as you can see here, we are having the stiffness. It is a little bit blur, I know, but anyway, I hope that it will work. Let me check something. Okay, so now here we have the forces, as we said, F1, F2, and F3, and we are having the individual, or we can say the free body diagram of each mass, floor mass, that is going to be represented as you can see here. Each mass is going to be acted upon by different types of sources or forces. The first one from the left is going to be the direct application of mass. The direct application of force, which is F1T. This is where the dynamic force is being applied, right? And whenever that we have something dynamic that is being applied on a mass, directly we are going to have inertia that is going to be developed, and this inertia is going to be in the different or in opposite direction of the dynamic force being applied. So we're going to find that the mass is going to develop M1 U1 double dot. Okay, this is what is going to be developed here. So we know now there is one force from the left, another inertia force from the right. This is related to the mass itself. these are the forces that is going to be developed from the application of the force and the inertia developed by the mass. But the columns and the motion of other masses are going to contribute to the forces on the mass, on this mass. For example, the first column here is going to resist the applied dynamic load, right? It is going to resist as if it is going to push the mass back, the force pushing it to the right, and this column is going to, or as if it is acting to return the mass back. So we're going to find K1 U1 here, and it is opposite to the application of the force. So this is K1 U1. This is elastic resistance. Okay, now from the top column we're going to find that there are 2 points we need to consider. The top column is having motion at its top end by U2, and there is a motion at its bottom end by U1. So this means that the column is going to have some different, right? Different or relative movement, which is U2 minus U1 here, right? So this difference is going to be the resistance, or we can say this is the contribution of the top column on the mass number 1. And the direction is going to be to the right. Why? Because remember that this force, which is being applied on this mass, second mass, is bringing this mass here. So this means that this column, as if this column is taking the mass M1 also to the right. Okay, so this means that the application of the we can say the force on the second mass is going to make the resistance of this column to be in the right direction. So we're going to have K2 times U2 minus U1. Okay, so this is what we are going to have. Okay, and in a similar fashion we are going to describe the equation, or we can say the equilibrium equation for, or the free body diagram for the second mass. We have force applied, we have inertia developed, we have resistance from the column below, and this resistance is K2 times U2 minus U1. As I have explained, it will be the same exactly as what we have put here on mass 1. And in the top, it is going to be the same, but instead of that, we're going to use U3 minus U2, and it is going to be acting upon mass 2 toward the right direction. Okay, so this is what we are having here. This is what we are having regarding each mass. Okay, so based on that, we can now go back and look to our equation. So now we can understand this shape. Now we can understand it. Okay, so the point here is that we are having forces, we have masses, stiffness, and we can get, or we can put the mathematical model. Now let's go to the mathematical model, and we are going to apply the coefficient, damping coefficient on it. Okay, the mathematical model here is considered to be a way for, or a mathematical representation of our system, a mathematical representation of our system. So we are going to put the first mass, which is the first floor mass, it is M1, as if it is like loaded on a cart like this in a trolley, and this is M2 and this is M3. Okay, we have 3 different masses representing 3 different floors. The first mass is related to the ground with two different ways. The first one is resistance K1 of columns, and C1, which is the damping of the first floor, right? And this is what we have mentioned here before. This is, we have here C1 and we have the resistance of the columns. Okay, so this is what we are going to have. Okay, and after that we are going to see that for this mass it is subjected to another type of so this mass is going to be affected or subjected to force, which is F1, and K2, which is coming from the stiffness of columns above, and C2, which is the damping of the floor above it. And we are going to have the motion to be with amplitude or displacement U1. Whenever we look to this, mass 1, which is considered to be floor 1, if we are going to cut everything and look to the free body diagram, okay, the free body diagram, we are going to find that mass 1 is going to move in this direction, which is U1, and it is going to move like this distance, U1, from the original position due to the application of the force. And we are going to have 5 different forces applied on this mass. Okay, we can say it is 6 actually, not 5. First of all, there is induced inertia force, which is M1U double dot. It is opposite to the applied force, which is F1, right? So these are inertia force and the applied mass, the applied force, which is function of t, function of time as well. And then we are going to have K1 U1, which is the stiffness resistance related coming from columns. Okay, and then we have C1 U1 dot, which is related to, this is damping. This is damping force. This is coming from the stiffness, okay, of the floor. Stiffness resistance, elastic resistance, and this is damping resistance. And always their direction is opposite to, as you can see, to the force that is being applied. And then if we are going up, which is going to the upper floors, we're going to find that it is there are forces being applied on the same mass, but instead of using the absolute U2 or absolute U1, we're going to take the difference between the two. So we have K2 times U2 minus U1. Okay, this is going to be the effect of the second floor on the second mass, Okay, so the effect of the stiffness of the second floor on the first mass. And in a similar fashion, we can say this is C2 times U dot 2 minus U dot 1. It is the effect of the floor damping, floor number 2, or the damping or the second floor on the first mass. Okay, so that's how we can understand the mathematical model and the free body diagram. If we go to the second mass, you're going to find it similar, in a similar fashion. It would go in this direction, U2. As you can see here, this is U2. And we are going to find that this system is going to, or this mass is going to be subjected to forces similar to mass 1, but they are going to be different in magnitude. So we have F2, which is the dynamic force being applied on that floor or in that mass, which is F2 in our case. And then we have inertia forces, or inertia force, which is M2 U double dot 2. And then from the left, we are going to have the same as we have done before. The same as we have done before. Okay, so this means that we are having K2 times U2 minus U1, and we are going to have C2 U dot 2 minus U dot 1. This is from the left side of the mass. Okay, and if we are going to talk about the right part, okay, here, and here, we are going to find that we have K3, which is the third floor, times U3 minus U2, which is U3 minus U2. Again, if we are going to look to what we have done before, here we are talking about the differences. This is, yes, U3, okay, U3 minus U2, as we mentioned before. It is the difference between the displacement at the third floor and the displacement of the second floor. Okay, this gives us the meaning of the forces being applied on the second mass. Okay, and in a similar fashion, we are going to find that the forces that is going to be applied on third mass is, as you can see, the force applied, dynamic force, and the inertia forces. And after that, we are going to have the same forces going to be applied on the second mass. It will be applied on the third mass, but in different direction. Okay, and we have the forces here. After that, we do not have anything here. Sorry for this. We do not have anything to be applied on this mass. Okay, after that. Okay, this is what we call it the free body diagram. It's pretty easy and straightforward in order to put the equilibrium equation for each mass. Okay, we're going to look to each mass and we are going to put the equation or equilibrium equation for each mass. Let's put this. This is for mass number 1, which is floor number 1. Okay, this is floor number 1. So here we are going to put everything on an equation, as you can see. So it is going to be M1 U1 double dot, which is the inertia force, and plus C1 U1 dot plus K1 U1, which is this term, and then we're going to have two minus terms here, which is going to be related to C2 U2 dot minus U1 dot and K2 times U2 minus U1 dot, as you can see here. We put everything in the left hand side. Okay, so we assume that this direction is going to be positive, and then in the left hand side we put all the forces related to the masses, the stiffness, damping coefficient, and the displacement, velocity, and acceleration. And it's a common practice to put the force to be on the right hand side. Okay, why we arrange them in this way? Because it is going to be easier for us and informative when we are going to deal with it mathematically. Then we're going to find that our equation of motion, or this differential equation, is going to have something common on the right hand side, which is the application, the force applied, and the right hand side is going to have the derivatives of the main response parameter that we are seeking for, which is u. Okay, so this is what we are going to put it in a way that we're going to put it. Now for floor number 2, look to this floor number 2, and from these we have like 1, 2, 3, 4, 5, 6. We have 6 terms, 6 forces are going to be applied. 5 of these terms are going to be on the left hand side, and the force being applied only is going to be on the right hand side. Okay, so I can check them one by one. First, it is related to M2U double dot 2, and then we have the forces coming from the second floor, damping forces and elastic forces. This is damping force, elastic force coming from the second floor, and then we are going to find the damping force or damping resistance and elastic resistance or stiffness resistance from the third floor, which is this term and this term. Okay, and take care, they are minus here, because we are, as we said, we are taking global lift to be the positive one. And then we're going to find that the right hand side is going to be the force being applied. The force being applied. Okay. Now the third, which is the third floor, it is going to be, again, the forces being applied is going to be 1, 2, 3, 4. 4 forces only. So we're going to find 3 terms on the left hand side and 1 term on the right hand side. Okay. So on the left hand side, the inertia forces m3u double dot 3 plus, then we have plus here because we are in the same direction. Okay, c3 u dot 3 minus u dot 2 plus k3 times u3 minus u2. This is the 3 equations or differential equations that is going to present the motion of this system. Based on that, we can put it in a form.